Why don't you kick us off?
Hello. So normally we show up with these things. That's what we've done so far in recent years with a working prototype. We've done the same this year. And before we show that off, though, we'd like to explain the issue. All working Mars rovers use a rocker-bogie suspension system. Everybody knows how that one works. It was developed at Caltech. It's a beautiful piece of engineering. And of course, we think we can offer an incremental improvement to it. Here's the problems with it. The main issue is that it has few points of contact between the rocker arms and the chassis. The second problem is that it requires either a balance bar to make sure that the rocker arm moves counteracting to each other, or a differential. Now, if you have a differential, it's going to sit in the middle of the device, so that cuts your payload bay in two. If you have a balance bar, it's going to have to sit on the bottom and get hit by rocks, everything else you want, or it's going to be on the top and get in the way of your solar panels. The other problem is that the differential or the balance bar must support the entire weight of the device. You only have 2, maybe 3 points of contact. They get all the stresses, they get all the lateral stress, they get all the problems. That shortens the life of the rover. Now, this has not been an issue for Spirit and Opportunity, but it may be an issue later on, because eventually we're going to have crewed rovers. They're going to have to carry different type of things. The other issue is, good.
So the thought behind that is that when you have a rover getting bigger, the analog to a bigger rover in Martian gravity is a smaller rover in Earth gravity in many ways. So building this suspension system and testing it so that it is performative on Earth gives us insights into how we can build a larger rover that could, for example, as MK said, carry crew on the surface of Mars sometime in the future. And that's kind of what got this going. Was rocker-bogie rovers aren't really something we've been able to use all that effectively on Earth. And the single point of contact in Earth gravity is one of the bigger drawbacks to why they don't scale up very well. And we think we've got a way around that.
The other issue is that all the rocker-bogie rovers that are deployed right now have to have a wrist actuator for the wheel motors. So you have 6 weak points. You have 6 actuators that can get stuck, which is what happened to Spirit. You have, in addition to it being a weak point, you have a point of complication, because you need a roller bearing, you need a motor, you need something to deal with any lateral stresses, you have something that can bend if it bumps into something, and it will, because it's holding up a wheel, so it will bump into things. So skid steering has always been an option, but it's always been the backup option. That skid steering with a rocker-bogie rover is something you do if your wrist actuator has broken. Here's our solution. Extremely simple. We're going to waste half an hour of your time on something that is so simple, you're going to laugh at us when you see it. But, you know, it's like Leonardo da Vinci said, the best system is not one from which you cannot add anything, but one from which you cannot subtract anything. What we're going to do is we're going to go back a few thousand years and use a block and tackle system like you would on early sailboats, or in fact, modern sailboats. Very proven technology. It's been around since the times of Ulysses. It's just a little piece of rope going under the chassis using a drum, and it can sit outside the chassis. It's going to sit at the corner of the chassis. In fact, you'll see it in a minute. It is under the chassis, like the problem I said with the balance bar, but it's very easy to armor, because the only moving part is the rope itself, which needs only a little bit of passage, and a drum. So that gives you a situation where the weight of the rover is supported by 10 points instead of 2 or 4. Specifically 2 per drum, the 4 drums, 8, and the original 2 at the semi-axle pin. And here it is.
That's a very simple example of how it's moving. You can see that at the top of the rocker arms, there are no bogies attached right now, that a rope is attached that passes underneath the rover, around the drums, and attaches to the opposite point on the, or to the same point on the opposite rocker arm. By attaching those at both ends, this creates counter rotation the same way you would with a balance bar in the opposite rocker arm.
It also does a couple of other things. For example, it introduces a little bit of lateral pull, which we will explain later. Like I said, we could end the presentation here. This is an extremely simple mechanism. Now let's see how it does. Let's see how it behaves itself.
Oh, you've left the presentation.
I think I've hit escape once too many. There we go.
Yeah. Skip the video. It's not escape to skip the video.
So skid steering, why does it help us? Because the rope pulls the arms inwards a little bit. So what that does is that it redirects some of the lateral strain. It prevents this kind of splay that you see here.
I can show a bigger example, I think. Here with
Excellent.
this larger rover, you have these two very long rocker arms. And while they splay outwards, there is force acting here at the drum, pulling these rocker arms inwards. This splay in the version without had, I could go out to probably about here, about 50% further out with this tire. And this is just using 3D printed materials. If this was aluminum, this wouldn't move at all.
This gives us something that can skid steer as its primary method of steering. That's great because what you end up having is something that is simple while not being underactuated. Now note here, this was taken out. This is intentionally underpowered. This was taken out of a little RC toy. It's supposed to only drive 2 of these TT motors. It's driving 6 because we're not here to show off motors. We're not here to show off a controller. We're here to show off a mechanical design. So all the tests you're going to see are with something that is supposed to drive about 30% of what it's driving now. Most importantly, you only need 2 motor channels, left and right. No wrist actuators, no wrists, extreme simplicity. So that gives you a couple of things. One, less mass budget for the steering mechanism means more mass for the payload. The mass you're saving for your drive system can give you another drive system. You can have a redundant system here now. In addition to that, you can also have a redundant system. As for how it does skid steering, let's give it a difficult surface, namely a carpeted couch.
Just for reference, these tires that are being shown on this robot
are terrible.
Yeah, they're normally used for elementary school and high school educational robots. They cost about 20 cents and they do not grip. These tires are awful. We specifically chose to use awful tires to demonstrate that this thing can skid steer, even with, as you can see by how much the wheels are spinning, probably less than a 50% grip ratio there.
Note that there is no splay. There is no movement. And this is not because this thing has been pulled very tight. It's just because the drums are doing their job and they're keeping the rocker arms together.
The closer the drum is to the end of the rocker arm, and the shorter the bogey is, the less you will get splay. The more effective this mechanism is at reducing the splay of the rocker arms. So with this specific design being the same length as the body, and the bogey's only extending about 10%, 15% the length of the rocker arm.
About 15%.
Yeah, you're not going to get really any significant splay at all. And that is a viable design because the JPL reference implementation only extends the bogeys about, what, 20%? About that. I'd have to get the measurements, but it's in that ballpark.
Okay. There we go.
So here's an interesting thing that I played around with a bit, which was the Antbot design, which is Robots Everywhere's flagship robot, has tracks with 2 endpoints and a semi-loose track in the middle. So I said, a bogey kind of looks like an Antbot. What if I made tracked bogeys? And in this case, this isn't a rocker-bogie suspension. This is a rocker double bogey suspension, which was first pioneered by some guys at, I believe it was Carnegie Mellon, but has been back and forth for Mars rover proposals, at least to my knowledge, since 2014. But this is an interesting implementation because until now that I've seen, nobody's really looked at what if we use a half track. And just from messing around with it with some servos for power, this thing climbs great. The grip is exceptional. It has very similar performance to an Antbot in that it can run on rough terrain, it can move up and down dips, and it can climb over heights up to, that cushion is almost as tall as the robot itself. And while it does need to find some assistive terrain in that foam block, it wasn't able to climb that slope on its own with nothing assisting either wheel. It still is able to navigate this terrain, which is significantly taller than the height of the bogey.
And one thing that's important to note is that this system here with the 4 half tracks is still only using 2 motor channels. The electronics are roughly the same. This one is, I believe this one is using either a propeller chip or an ESP32.
That's an ESP32.
But it's only moving 2 channels. Everything else is passive. There is no method to adjust the arms. There is no method to let it adjust the bogies either. This is all passive. This guy is very under-actuated, and that's the way we wanted it.
Yep. This chassis here that I used in the original demo of just showing the mechanism, this is what I put those track bogies on. That's all it is.
Now, the one you see here, for the demonstration you saw earlier, and for the ones you're going to see next, I wanted to put some payload on it. Specifically, this guy, as it is, weighs about 135 grams. So we put an equal amount of mass in the form of ball bearing balls in the payload bay. And one thing I want you to note is the payload bay is fully accessible. There is no differential in the middle. There is no balance bar at the top. There is nothing to get in the way. If you were to load this thing, you could. If you need to have an instrument that has to have a certain shape, it does not need to be constrained by the shape of the cargo bay any more than knowing just how big the rectangle is. You saw some climbing earlier. You're going to see some more climbing now. Note that this thing will go up something that is taller than the height of the wheel. There is no loss of performance, cargo capacity, movement. I would dare even say resilience compared to what exists right now. So where's the catch? There's always a catch, right? This video is a little long and we're probably going to cut it a bit.
Yep. But we can show it going over this battery box without any difficulty at all. Just zip, zip.
By the way, that's a 4-wheeler version in the back there, which we will not be showing running because this uses micro motors. And while it does move, it cannot climb because it's basically using motors that run off 3 volts at approximately 30 milliamps. That was a little bit too little. What I wanted to show here is that this thing can climb just fine coming and going. And I wanted to show that the mechanism moves as it needs to. There isn't terribly much to say about it. So I think we're going to forge ahead. Once you've seen this run once, you've seen this run several times.
Yeah, we're a bit behind on time. So yeah, let's skip to the juicy bits.
Let's move on.
So we were talking a bit about the catch. And one of the things that we could say is the catch that we know about is that we're using rope or cable underneath the rover. And Martian grit, for example, could be very hard on rope or cable. Now, first off, we could replace this with a chain segment. And at that point, grit is only harmful to the chain links. And that can be minimized with a coating. Various coatings exist to minimize grit adhesion. And secondly, this catch isn't as big of a deal as it sounds because rope, chain, cable, these things are easy to repair. Chain link connectors can be repaired in the field very quickly. Rope can be spliced, rope can be tied, cable can be sleeved. And for a crewed rover, this becomes very easy for a crew to perform a field repair. They bail out of the rover, they get their toolkit out, and they could be back in motion in under 15 minutes.
In addition, this system gives you an opportunity for redundancy because, for example, see this asymmetrical rover here. You could have an extra pair of drums here and here, or even here and here, and they could be doing their part to hold up the weight and also to keep the mechanism running in case one of them breaks. The other thing you could do is simply have two ropes. In this case, we got 4 drums, but 2 rope segments. I don't know if you can see it. 2 rope segments per drum. One breaks, you're still good on the other. Now the rope or the chain will eventually slack, but what you could fix this having one actuator. Turns out you only need one for the entire rover to just reel the slack in. You can also use that to pitch the rover up and down during normal operation if you want. Now that does add an extra actuator, but remember, we're still replacing it. We're still going with -6 or 8, one per wheel. As for climbing, I said I was going to show it to you climbing something taller than itself, and here it is.
This is a step up to the back of the shop.
Note that we do lose some marbles here because this thing is steep and this thing was full of marbles, but it gets there.
If the payload bay were covered, there would be no issue. This is climbing at about a 50-degree angle.
And that's me recovering it.
And then in reverse, going down.
And there we go. I lost my marbles.
So we've got a couple more climbing demos that we can show.
There we go.
It goes up one more time with a bit less payload. Yeah, we're back on track with time.
So what's the whole point? The whole point here is flexibility. We make the rover in such a way that the payload folks can do whatever they feel that they need to do. You've seen it climb. You've seen how compact it is compared especially to balanced bar systems. You've seen it run on 6 wheels, 8 wheels, 4 tracks. The other interesting thing is that swapping the rocker arm is very easy because the pins are not connected to anything. You just unscrew, replace, screw back in. You're probably going to have to adjust the ropes, obviously, even those they're only held up by 2 pins. Now the other rover has 4, 1, 2, 3, 4, but you only really need 2. They can be at any place on the rocker arm. again, ease of repair, ease of replacement,
and ease of redundancy. So speaking of redundancy, I built another one. This is the same little RJP we built. This is the big rover that I was demonstrating the splay on. I have this one on a tether right now because the device I am using to film the robot is also what is normally that robot's brain. So one of the things we develop is Android robotics, and I'm filming this from the phone that normally runs that Antbot board. So this is just a little back and forth across the books showing that this can climb obstacles. This was the first prototype of this mechanism that we fully constructed. And here we have some ice packs. Now, the ice packs that are shown on the left side in green, those are warm. They are gel. The ones on the right in blue, those are frozen and extremely slippery. So watch how it handles this. With a combination of skid steering and forward acceleration, it's able to navigate around this obstacle at speed.
This is much harsher terrain than anything that has been navigated so far. This guy is
quite the goat. There it goes, up and over.
We're repeating this a few times just to show that it's not a fluke. The logic used to figure out when to climb is that there is no logic on this one. This is just an RC. But what I did was I'm just going to pretend I'm running a simple algorithm here. If I am stuck, reverse a little bit and then try again. Do each sponson alternate to do that. So even the navigation algorithm to handle complex terrain can be very simple. Now that's less of an issue these days, but like again, what's not there cannot break. Note that it is climbing something pretty much as tall as itself or taller than itself, not just taller than the wheel. As for why the other side is basically a gel, is that I wanted to see how it would do with soft terrain. I wanted to see how it would do with sand, dust, that kind of environment. We'll make these videos available. We're probably going to make the designs available very soon. The other thing you can do is that since there is no differential and no balance bar, you can put stuff in a pickup truck configuration. This is going to come in handy when it's time to build on Mars. We're going to have to carry prefabs. We're going to have to carry trusses. We're going to want a pickup truck. The other thing is that you can have the crew can ride front, rear, wherever they like. The back part here can be used to hold somebody prone. This thing makes for a pretty good rough terrain ambulance if needed. That's actually something I'd like to see developed here, because a lot of places would like to have a heli ambulance but can't afford it. Imagine having a few of this in national parks, for example. The ease of repair we've already covered. On that note, this one has been broken by me stepping on it. You can kind of tell that there's this big old knot that I did, because what you want to do for field repairs is essentially have maybe another meter or two of this rope, which you're going to want around on a rover anyway, because rope is useful for 3,000 things. You just splice it in, pull it in, give it a bit of tension, and you're back on the knot road. Other important thing, and I want to show you this. This has been printed on a $300 3D printer from 2014. You can kind of tell this is a very rough surface. You do not need a precision machine differential. You do not need a precision cut balance bar. You don't need precision anything almost. Why? Because the idea is that one of these can be printed in 2 shots. Everything else can be made out of nails. And in case of the one you saw moving, it literally was the only non-3D printed part here are the motors and a bunch of nails, the wood nails. Everything else you can print, everything else you can improvise. Even the rocker arm can be just a piece of, it can be just a piece of aluminum with holes in the right spots. You can put one of these together by hand. You can jury rig something. This machine is very resilient. There will be a point between when Mars is colonized and when Mars is civilized that you will want things that are easy to jury rig, because you will be operating in a hostile environment. You will be operating in an environment where your equipment is what takes you home. So you will want to be able to do something with it as you are, with big gloves on your fingers, because there's no air right now. You want something flexible.
Thank you, MK. You and Riley have ran out of time.